Now, let's take a little bit of time to understand what machine learning is. Machine learning, I just told you, is learning about the world. Learning about the world, usually from data, right? You could learn about the world without data, in which case we don't really call it machine learning. But how do you learn about the world from the data? And what are the challenges in doing that? So here is the deal. So we make a huge assumption that the past is a good representation of the future. The past is a good representation of the future is an assumption we make. And now if you do make the assumption, you can simply say, hey, whatever I inferred in the past is the future, but that would be too strong an assumption. Just because it rained yesterday doesn't mean it's going to rain tomorrow. So it's not that when I say the past is a good representation of the future, I don't mean in that exact way. I'm not stretching that argument too much and saying the past, which is yesterday, is the same as tomorrow. I'm not saying that. However, I could weaken that statement and say, hey, if in the past 5 years, on an average, it's rained 1 out of 20 days, which is 5%, then I could make the assumption that, yes, tomorrow the chance of rain is 5%. But that could be a simple model, but that's a more reliable model than saying if it rained yesterday, it's going to rain tomorrow for sure. Agreed? Yes, if it rained yesterday, I might increase that 5% to a little more, depending upon what kind of pattern I found in the past. So in the past, I might actually put a little more insight into it and say, hey, what are the probabilities that if it rained on a given day, it rained the next day too? And that is like 40%. Then I might say, hey, now given that it's rained today, tomorrow has a 40% chance of raining, something like that. So as I go through that rain example, you'll realize that what I'm trying to do is I'm trying to understand the past. The past is amalgamation or a fusion of two things. It's information and noise. Right? There's information in the past, which is on average how many days does it rain? That's information. And there's noise in the past, which is on a specific day, it just happened to rain or not. It's like tossing a coin, just happened. So this is like tossing a coin. Information is the fact that I have an unfair coin. If I toss it 100 times, then I realize that there's a 70% chance of head and 30% chance of tail, an unfair coin. And that's why I have to toss it so many times to figure out what the heads versus tail is. But then the noise is exactly what happened at the 10th toss. It doesn't really matter what happened at the 10th toss. It just matters what the information is, which is the average head possibility of head and average possibility of a tail. When I'm given data, I'm given a sequence of coin tosses. I'm given heads, tails, heads, tails, heads, something like that, right? Now, from this, I infer that 70% heads chance, 30% tails plus noise, right? So this might not be exactly 70-30, meaning for every 7, you're not going to get every 3. So now, if I look at this sequence and average this out, I know it's a coin toss, so it's a simple example. I average this out and say it's 70% heads and 30% tails. That's what I mean by information. Noise is everything that is just around that information that is not predictable, that's not something that I expect it to repeat itself. Then I say, once I've identified the information, I say information is going to repeat itself. Of course, the future is going to have its own noise, but this noise is not going to be the same as this information is going to be the same as this information, but this noise is not going to be the same as this noise. No, that's not going to be true. Meaning, yes, I do expect 70% heads and 30% tails in the future too, but just because the third toss was a tail, I cannot expect the third toss in the future to be a tail. That's what is noise. We will still have noise in the future, but the noise will not exactly repeat itself like the past, but the information does. This is the information. So now, machine learning is all about looking at the past, making that assumption that at least a part of the past will repeat itself, and that's the part that we call information. And how do I create a mathematical model like this one that captures only the information, leaving out the noise? If I can manage to do that, then that's what machine learning is all about. I need to automate it. Unfortunately, we don't have the data is present to us with both together. If the data was present to us in two different components, then we don't need any fancy technique, but now we do. Now, in machine learning, people use the term, you'll see this in the introductory machine learning course, you'll use the term underfitting versus overfitting. You know, that if you capture much less of the information than is available to you, we will call it an underfit model, meaning it doesn't capture as much as information as it should have. But sometimes machine learning models become so complicated that they not only capture all the information, but they end up capturing noise. Then we will call it an overfit model. Clearly, both the underfit model and the overfit model are bad. Underfit model doesn't capture enough information for prediction, and the overfit model captures the noise, which will not repeat itself, so it ends up making bad predictions too. So the challenge in learning about the world from data is making this very fine balance between overusing the past data and overfitting it, or underusing the past data and underfitting it. And how do we do that carefully? How do we do that precisely? How do we do that in a comparable way is all that we will talk about in machine learning.